So last week, if you recall, we discussed about the RAM technology, resistive random access memory. And today we're going to switch the topic a little bit on a new emerging device technology based on ferroelectric material. And we believe this is a promising candidate for implementing the computing memory hardware accelerator. All right, so then let's get started. This is the outline of today's presentation. First, I will go through some fundamentals of the ferroelectrics, and then we will talk about the device structure, and then some device physics, and then the device level operation, and the variability and scalability. And after that, we will talk about the applications of the ferroelectric devices for computing memory. And we have three applications. One is for megabyte level AI model inference, then AI model training, and finally we target at ultra large model. So here the model size could be up to gigabyte or even hundreds of gigabytes, where the 3D NAND version of the FeFET will be very useful. So then this is the starting point. So let's have a quick recap. I believe we showed this slide last time. So here are the emerging number time memories being pursued in the industry right now. And the first three are two-terminal resistor devices. So we can have the RAM, as we discussed last time, where we can create this filament between two electrodes to have the filament connecting electrodes, or we do not have the filament connecting the electrode. Therefore, we can have the low resistance state and high resistance state. And then we have the magnetic tunnel junction and the basis of the MRAM, depending on the magnetization orientation between those two little magnets. Then we can have the anti-parallel and the parallel configuration. Then we have the high and low resistance states. And then phase changing memory, again, based on the chalcogenic material, and then depending on the orientation or the crystalline phase of this material, we can have the low resistance state or amorphous phase, then we have a high resistance state. So here, today's topic is on the ferroelectric, and one of the ferroelectric device structure is this ferroelectric field effect transistor, FeFET. So here we replace the gate stack of the normal MOSFET with the ferroelectric material, where we can have this spontaneous dipole built in to the gate stack. Therefore, the channel threshold voltage will be tuned by the direction of the dipoles. So we can have different conductance of the channel depending on the threshold voltage. So then we can have multi-level states as well. So today we will focus mostly on the ferroelectric devices, and it's a three-terminal in this configuration. So the operation will be a little bit different from the two-terminal resistive memories. So let's have some review of the basics of the ferroelectrics. So this is from the college physics. So we have the dielectrics where we can have the ionized bonding between those atoms. And then the ions bonding, will have this ionic bond between the atoms. And then when we apply the electrical field, then those ions, the dipole, essentially, will be aligned with the electrical field. And in the normal dielectric, after we remove the external field, then the dipoles will be randomized after the field is removed. Then in the net, a charge at the surface will be 0 because those orientations will be randomized. But the ferroelectric is a special subset of the dielectric, where after we remove the electrical field, still the dipoles will be aligned in this direction. So this will be still aligned. And therefore, if you look at the surface of the material, then on this side, you have the positive charge. On the other side, you have negative charge. So this net charge at the surface is called the polarization. So essentially, this polarization has a unit like a microcoulomb per centimeter square. So this is the number of charge divided by the surface area. So this is the unit for the polarization. And here, this ferroelectric has this property. That is, after the electrical field is removed, we still have the surface charge. So that's ferro material. So here, historically, ferroelectrics has been discovered like more than 100 years ago. And most of the prior research of the ferroelectrics based on the perovskite material, like PZT, SBT, very complex oxide, like a 3-element or even 4-element. So those ferroelectrics in the old days are not very scalable. So to show the ferroelectric property, then the thin film needs to be thicker than 100 nanometer. So this is not very compatible with advanced CMOS technology. That's why the perovskite ferroelectric devices have been commercialized before, because if you look at those simple like your ID card or this hotel room key or something like that, actually has the ferroelectric memory built in, and those no cost, one time or few times use for those like ID card. The data is stored in FeRAM in those ID card. And those technologies are based on the old perovskite ferroelectrics. And the best technology you can do there is like 130 nanometer load for the peripheral circuits. So it's not very scalable to today's advanced CMOS. And then things changed around like 2011. So there was a paper published by NAM Lab, which is a research lab in Germany. And it discovered that in the half-link oxide material system, we could have the ferroelectric property as well. So here the key is that to form a very particular phase in the half-link oxide system, which is called a orthorhombic phase, which we show here the crystal structure of this phase. And here you see this red ball is the oxygen atom, or let's say ionized oxygen ion. And then here on this one, this is mostly half-link ion. But sometimes if we replace this half-link ion by other dopant, such as zirconium or the silicon or aluminum, then we can have this kind of stable phase depending on the atom configuration. So one is like this oxygen ion is down here. The other configuration is that the oxygen ion is up here. So they have those two stable configuration. Therefore, internally to this unit cell, we will have the built-in like a dipole of pointing up and pointing down depending on the atom configuration. So this is the root cause for the ferroelectric behavior in the half-link oxide system. But half-link oxide has so many phases, so we have to make sure the half-link oxide is stabilized in the so-called orthorhombic phase, where we can have this ferroelectric property. So then half-link oxide, of course, is very welcome for the industry, because for today's high-k metal gate transistors, below like the 45 nanometer. Then all the logic transistor you use today, including today's FeFET, then the gate stack is half-link oxide. So it's adopted in the manufacturing already. That's why the CMOS compatibility makes this technology very attractive for the industry. And then you may wonder then why previously, for the logic transistor, we also use half-link oxide, but we don't call it a ferroelectric field effect transistor. So there is a difference here. So for the logic transistor, okay, we use today in your product, then the amorphous half-link oxide is used. So the gate stack, even though it's half-link oxide, but half-link oxide is in the amorphous state. So there's no crystalline structure like this. So then atoms will be more random in that case. So we do not have this net charge in that case. But if you crystallize the hafnium oxide in this particular phase, then we will show this ferroelectric behavior. So this is a key difference. So the logic transistor use the amorphous hafnium oxide, and here the ferro will use this Horst-Hornbeck phase hafnium oxide. And then here is the polarization versus the electric field. This is how we characterize the ferro property. So basically, if you measure the surface charge, then you can have this hysteresis loop. So here, then you can apply a positive voltage, then you polarize up the dipoles, and then sweep the voltage back to the negative, then you polarize down the dipoles. So then at 0 voltage, this is after you remove the field, then you could have the two states. Then you either the dipoles are or pointing up or pointing down. So you have this so-called remnant polarization PR, which will characterize the the window for the memory operation. So here we show this positive up, negative down switching. The reason is that when you apply the actually the electric field, there are two components contributing to the charge. So how do you get this figure? Then you basically measure the current in the time domain and integrate the current with time, you get the charge. So here, the total charge has two components. So here, the first one is this linear component. This is like your normal dielectric. If it's normal dielectric, then you have this linear curve between the polarization versus the field. This is like you're charging and discharging the cap, basically. And then on top of that, then we have this black curve, which is the ferro switching. And then the ferro polarization switching plus the charging component, because the total charge, which is this red and the blue curve. So this is how you incorporate this plot. Okay, so then if we integrate the ferro to the gate stack of the MOSFET, it becomes the FeFET. So what are the fundamental mechanism of this FeFET? So if you look at this figure, so you can program erase the ferro using a positive gate voltage or negative gate voltage. So you have a large positive gate voltage, then basically push all the dipoles pointing down. So the positive charge will be at the surface of this ferro gate, which will induce the electron inversion from the channel. So here, typically the FeFET is based on NFET. So here, you need the channel inversion to get the electrons. So since you have positive charge at the surface, then it's easier to induce the channel inversion. So in other words, the threshold voltage is lower in this case. Then if you polarize up by erase, use negative voltage, then all the dipoles are up. Then you have a negative charge at the surface. Then this will attract the holes from the p-type substrate. So this is like the accumulation mode. This means the threshold voltage is negative. So then here, depending on the threshold voltage, then you can have different ID VG curve. So then here, this is ID versus VG, and you can have multi-level states, because if you have all the dipoles pointing down, then you have the very negative threshold. Then if you have all the dipoles up, then your threshold voltage would be positive. But if you have the partial polarization, let's say some of the dipoles up, some dipoles down, then you have those intermediate states. So this is the basis for the multi-level switching. So here we can have multiple so-called multiple domains for the multi-level, because here in this gate stack, it's not one uniform ferroelectric thin film, because you may have some parts which is called domains. We can have those domains to be switched individually. So here, then we can use multi-level states to map multi-level weights, and so it's useful for the deep neural network inference. So here, FeFET actually has a very similar operation principle compared to today's charge trap NAND flash. And so here, flash also based on the threshold voltage change by charge trapping to the gate stack. So normally today, Sonos structure, you have nitride for the charge trapping. In old days, you have the floating gate, which is polysilicon. Anyway, so the flash transistor, also IDVG, will have this shift of the threshold voltage. But here I want to emphasize one difference, okay, between the FeFET and the flash. That is the switching direction is different. So for ferro, if you look at the switching, it will be like this counterclockwise switching. That means when you apply positive voltage, positive gate voltage, you are going to decrease. You are going to decrease the you are going to decrease the threshold voltage. And then if you have the negative voltage, gate voltage, you are going to increase the threshold voltage. So this direction is opposite to the flash. Flash is when you have the positive gate voltage, you are going to increase the threshold. Here in the ferro, you're going to decrease. So the switching direction is different. Or in other words, the charge trapping and the ferro switching will compete for each other. So that's why in ferro or FETs, we want to avoid the charge trapping. If you have a significant charge trapping, then in the memory switching, the memory window will be reduced because those two mechanisms will compete for each other. And then compared to the resisting memory, so here FeFET could be much lower write energy. The reason is that for the ferro switching, we're going to apply voltage through the gate, so there's no DC current. So it's like field driven. If it's field driven, then it's much lower energy than the current driven. Okay, so then here for the ferroelectric field effect transistor, here is the status in the industry development. Global Foundry, because they have the partnership with the NAM lab who discovered this ferro initially. So they have licensed the technology. So they have started the risk manufacturing of the FeFET at 28 nanometer and 22 nanometer technology node. And it's pretty mature process from the Global Foundry. So here you see the diphoto and then the cross-sectional TEM for the ferro from the Global Foundry's 28 nanometer platform. So here the gate stack, if you zoom in, then you have the doped silicon and hafnium oxide. So here, then this is a front-end of line integration. So because here the ferroelectric is inserted to the gate stack of the transistor in the front-end of line fabrication. But also you can do the ferro fully back-end of the line. That means we do not use a silicon channel. At top of the interconnect, we have other channel material, for example, the oxide channel, indium oxide channel, which is a semiconductor as well. But we can do it at lower temperature, so we can have the back-end line integration of the ferro FETs as well. For example, Intel reported a paper, IDM 2020, with this back-end line approach. So here, I would say that for the front-end line integration, mostly you have to use this silicon doped hafnium oxide. The reason is that the silicon doped hafnium oxide need a very high temperature to anneal the crystalline phase, as I said earlier. So if you do nothing to the hafnium oxide as fabricated, it will be amorphous state, which is used in the logic transistor today. But if you want to make it ferro, first we dope some atom, in this case silicon, but you have to do a high temperature annealing to reach that orthorhombic phase. So here the silicon doping will require like 900 degrees C annealing to reach that orthorhombic phase. So this temperature is compatible with the front-end line integration, because the front-end line, source drain doping will be 1000 degrees anyway. So then for the back-end line, then it's a different story. For background line, at top of the metal, you cannot allow temperature more than 400 degrees C. So you need some hafnium oxide system that could be annealed at 400 degrees C, and here the cooling dopant will be preferred. This HZO is a widely used background line ferro material because you can get the orthorhombic phase only with 400 degrees C annealing. So here, then still FeFET has many challenges today, and due to variability, reliability, we'll talk about that more in later slides. But I have to say that in my lab at Georgia Tech, we spent quite some efforts in the past 5 or 6 years to set up the ferro fabrication capability, and we have done a lot of research in this domain. And this is the picture from our clean room with our ALD system, because many of those ferroelectric materials are grown by the atomic layer deposition, which is very critical for the ferro growth. So here we have our system for the HZO deposition, and also we have very good relationship with Global Foundry. So here the Global Foundry send us their wafer, and they're like 28 nanometer wafer or 22 nanometer wafer to our lab for the device level characterization. So here this is an image from my lab. And you see this is a 300 millimeter wafer, 12-inch wafer from Global Foundry, and we got the wafer from them, and then we have so many devices on the wafer, so we can do a lot of device testing. Okay, so then let's have some more detailed discussion of the ferro. So here, as I said, the old ferro is based on the perovskite, which is this typically PZT, a very complex system. So here then today's ferro is on hafnium oxide, as I said, orthorhombic phase. So here is a crystal structure, and I would say they have comparable remnant polarization PR value, but here are some differences. So the critical switching field, the coercive field in the PZT is pretty low. Therefore, you need a very high thickness to show the ferro property. And then hafnium oxide, the EC, the critical field is higher. Then even with a very thin, like 5 nanometer thin film, you can still have the ferro. So this is a difference. But the epsilon value is lower in the hafnium oxide system. This is permittivity, dielectric constant. Then it's typically 30. So here, this is the pound measurement I mentioned earlier, positive up, negative down. So what you do here in the testing, if you have ferro capacitor, then what you do is to apply the voltage waveform, which is a triangular waveform. And then you measure the current, which is a red curve, is a current response. So you have this kind of current response from your measurement system. If you do the real-time measurement, your input is the electric field, the triangular waveform, and then you will record the current response in the red curve. So you do 2 positive sweep and then 2 negative sweep. Then you can get the curve, what we show here. So first, the positive sweep will create this red curve. If you integrate, so here you get the current, and then if you integrate the current with time, current times time will be charge. So if you integrate that, you get the polarization switching. So here, then the first curve corresponds to here this red one, and second one, because the ferro is already switched, then if you do it again, you will only have this capacitor charging. So you get this one. So this is positive up, correspond to here positive up. Then if you subtract those two, you get the real ferro switching, which is a black curve. So this is how you get the real ferro switching behavior, because you have to subtract the regular capacitors charging effect. So here are some values in this PV plot. So here P versus E electric field plot. So here PS is the saturation polarization. This is maximum polarization. This is maximum surface charge, basically. Then PR is the remnant polarization at the field 0. And then cursor field is somewhere here. So this is the critical field to trigger this switching. So here in the half oxide system, this switching is typically gradual. But in some of the PZT system, old system, it's a very sharp transition. The reason is that for half oxide, we have so many domains. So each domain may have a little different cursor field. Therefore, cumulatively, you will have a gradual switching. So here, this is another measurement, typically on the ferrocapacitor. So this is small signal CV. And this is not the large signal switching. So that means here at each DC bias point, we're going to apply a small signal, like a 30 millivolts AC signal to measure the capacitance. And then you have the double peak, typically in this small signal CV of the ferro cap. If it's normal cap, then it's a flat, basically it's a flat with voltage. But it's ferro, then you have this double peak feature. Okay, then the ferro endurance. So how many cycles can you switch the ferro? The dipoles up and down. Then here, typically you will have this so-called wake up and the fatigue phase. Initially, the PR window, the memory window is small. As you cycle in into some, then you can open the window, but eventually the window will degrade. So here the window means here, if you do the P and the E, then that is the window is the the PR, positive PR minus negative PR. So this is a window for the memory. So then there are many mechanisms ongoing for this kind of endurance behavior. Mostly are associated with the defect migration and defect generation. So here then, as we of course increase the temperature, then you are going to accelerate the degradation. Typically, without tricks, you can easily get 10 to the power 6 cycles of the endurance. But if you with special treatment, then you can reach even 10 to the power 11 or 10 to the power 12 cycles, as recorded in the literature. Okay, then we will talk about some device structure in the next. We already mentioned some of those FeFET behavior, but let's look at another device structure that is called FE-run. So FE-run is a little bit different from FeFET. So here the ferro cap is integrated to the drain of the transistor. So it's like today's DRAM, 1T, 1C. But today's DRAM C, here the cap is a regular cap based on the dielectric. But here FE-run is going to replace this regular cap with a ferro cap. So here then it's very similar, but then there are some differences. First is here this is the non-volatile memory, and because we have the ferro behavior. However, here the let's say the read is still destructive. That means every time when we read, we have to write the data back, because every read will destroy the data here. So it's the active write back for the FE-run. DRAM as well, we have to write it back through the system. So the first generation FE-run, as I said, stopped scaling at 130 nanometer. So for this low-cost ID card, then you still have the FE-run product using the low-cost fabrication platforms. But if we want to scale the FE-run in more advanced node, we need a 3D structure and change from the PZT to half-oxide system. So here then for the FE-run, the read operation. So this is the timing waveform, how you do the read. I'll skip the details, but then the key idea is that depending on the data you store here, you just say data 1, data 0. Then when you read, you have to write it. The reason is that you have to apply large voltage larger than the cursor field. So depending on the data you store, for example, if you store data is 1 here, when you apply large voltage, you are going to polarize up and then comes back. So when you progress up, then there's a switch associated with this polarization switching. So then if you measure the current, you have a large current from the cap. This is because you change the dipoles from down to up. So then you get a lot of current. But if the data stored is 0, then it's like you only charge up this part, there's no switching. So only the charging effect. So you get a transient current according to the non-switching charging effect. So you can differentiate the current by the sense amplifier. Then you can detect the data 1 or 0. So this is why every time when you read, you are going to flip the data 1 to data 0. So that means you have to rewrite this data 1 back. So you have to play with the timing a little bit. Through the other side of the capacitor, you have to write it back. So here, this is timing waveform to rewrite the data 1. So I will skip the details of the operation, but here I just want to emphasize every read, you have to write it back. And this is the write operation timing, and it's straightforward depending on the data. If it's in the data, we initially stored is 1. If you want to switch to 0, then you apply positive voltage, and to the capacitor here, then you're going to change the data to 0. Or if the data initially is 0, you apply negative voltage, then you will switch to data 1. So this is the write operation. So here, compared to the let's say the typical, let's say the FE run initial type market is to replace the NOR flash. So for those low cost, like ID card and this not high capacity memory, some low capacity, maybe kilobits, at most megabits, and low cost memory products. So here then the advantage. This is from the old generation FE run, so still separate so sell those products. This is based on the not hafnium oxide. This is still the PZT system. But even the PZT system, you see that it has comparable retention rate time with the NOR flash, but it has much faster read speed and lower operation voltage and much more endurance and lower read energy compared to the NOR flash. So it's quite competitive compared to the NOR flash for those low cost, low capacity memory application, like those ID card, for example. But then the new generation, as I said, so the hafnium oxide system based on FE run. So Sony has been pioneering in this field. They have demonstrated 64 kilobits HCO FE run at 130 nanometer. And so here, and this is their like summary for the performance of this chip. And so the rate voltage 25 volts, rate latency 40 nanoseconds. And then it sustains the retention at 85 degrees and endurance cycle 10 to 11 cycles. But here, this because Sony has a, it doesn't have the advanced CMOS platform. So it's 130 nanometer. But in principle, you can scale this to more advanced node. But you may have to use a cylinder-like structure to increase the surface area. Because if you stay with a planar capacitor, as you shrink the technology node, then the capacitor size will become smaller. Then you get less charge to read out. That means the sense margin is lower. So to maintain the amount of charge, you have to make this 3D structure, so still have a large surface area. This is similar to today's DRAM. If you look at today's DRAM, you have the cylinder like capacitor. So then this is a possible scaling path for Sony and FE run. And so of course Sony do not fabricate advanced memory at a lower technology node. But other company, I didn't include the slide because this is a pretty new, it's like a news just announced a few weeks ago. I just verbally say that. If you go to this year's IEDM conference, Micron is going to announce a 32 gigabit FE run chip. So this is much more advanced, 32 gigabit. And the technology node is roughly equivalent to like 28 nanometer also. So, and then Micron uses their DRAM process, essentially. Micron is a memory vendor, and then they change their DRAM process, and the 1T1C, this C is becoming the Ferro. And also Micron demonstrated the two-layer 3D stackable design. Their 1T1C, the T, I believe they use polysilicon, so they can do it at the top of the interconnect. So anyways, this is still I don't get the details of the paper because IDM is 2 weeks or 3 weeks away. So we still need to know more details after the IDM conference. But there is already a news about Micron's 32 gigabit FeRAM based on the hafnium oxide system. And then the other device candidate is FeFET, and this is what we already discussed earlier. I will skip this part of the slide, but here just to illustrate that the change from the normal MOSFET to the this is standard. Let's say take a standard high metal gate transistor and increase the thickness of the hafnium oxide system, and then anneal it, then it becomes a ferro. So it looks simple, but of course it's still a lot of engineering efforts. And then again, when dipoles pointing down, pointing up, then you can tune the threshold voltage. Then you can have the memory window defined as a threshold voltage change in the IDVG plot. So here, this is the GlobalFoundries 28 nanometer FeFET platform. And here, this is a typical IDVG curve. You have low VTH state, high VTH state, and the endurance cycling in the power 5 cycles, and the retention like 105 degrees C. So here you see that endurance is not so good compared to the FeCap or the FE1, which Sony recorded like 10 to the power 11. So here the GlobalFoundries FeFET only like 10 to the power 5 or 10 to the power 6. So there is a reason. I will talk about that in a minute. There's a degradation mechanism here. But GlobalFoundries already demonstrated 64 kilobit FeFET array. So here as a summary for the cheap performance, the program erase voltage 4.5 volts, and program erase uses write speed less than 500 nanosecond, read speed less than 25 nanosecond, endurance in the power 5 cycles. So then GlobalFoundries also extended the FeFET to more advanced node, like 22 nanometer, fully depleted SOI, we call FDX platform. So this is the improved IDVG plot from the 22 nanometer platform. So this is better because here this is the FDSOI platform. Then the channel is more confined in terms of the electrostatic property. And also GlobalFoundries demonstrated 32 megabits FeFET array with this FDSOI platform. And this is improved characteristics, especially the program time is much shorter, only 10 nanoseconds. But still the endurance is about in the power 5 cycles. And there's a fundamental challenge in the FeFET integration. I will talk about that in later. So this is the mechanism why endurance got degraded in the FeFET. This is because if you look at the band diagram from the gate to the channel, so you have the ferroelectric hafnium oxide. But then at the interface with the silicon, there is the interfacial layer called IL, interfacial layer, IL. So the interfacial layer is typically silicon dioxide, because here is silicon and hafnium oxide, then you cannot have the direct transition. So at the interface, the silicon will bond it with the oxygen from the hafnium oxide. So you create this surface or interfacial silicon dioxide. So silicon dioxide, if you look at the band structure of the silicon dioxide, It's much higher band gap. And then also the external dielectric constant, silicon dioxide is about 4, and carbon dioxide 25, 26. So here, then if you look at it's a 2 capacitor in series, and you will figure out that the most of the electric field will drop on this lower capacitance, no external material. So that means most of the voltage you apply from the gate will drop on the silicon dioxide instead of the ferro. So this is not good because you have a very strong field across the silicon dioxide. Then this will create the defect. You will break some bond, then create the oxide vacancy, essentially become a trap. So then you will have the charge trapping effect. That's why the no VTH state gets higher and higher, because as you operate the ferro, you put more and more electrons to trap into the surface effect. Then it becomes more like a charge trap transistor. It's like flash, as I said earlier. The flash and the FeFET red mechanism compete with each other. If you have more and more trap, becomes charge trap memory, then of course your memory window will become less and less. So this is the challenge for the FeFET, fundamentally because of this interfacial layer. And also there's a depolarization field that may impact the FeFET retention. So if you measure the retention, it will degrade over time. And this is because if you look at, it's still due to the interfacial layer. After the dipole flipped, then to balance the charge, here you will have some negative charge. In this case, if the dipoles are like this, then you have some negative charge to neutralize the positive dipoles here. So then this creates a field that is opposite to the dipole's orientation. This is called depolarization field. So this field internally to the device will tend to flip back the dipoles. So this will cause the degradation of the retention over time. And another challenge is the variation. So here if you measure the wafer, then you get the many devices. Then you plot the distribution of the low VTH state, high VTH state. Then you will have a wide distribution, and you may have the overlap. Then this will cause the error if you have low VT cross over with the high VT. The reason for this variation is because of the grain of phase variation. So the ferroelectric thin film has grown. It will have this kind of a grain boundary. So it's not uniform. And then after the annealing, then some of the parts may become the orthohombic phase. Some part will become other phase, or some part just remain amorphous. So it's not uniform. That will cause if you look at this is from the metrology under the microscope, there is some technique to measure the polarization or the phase. Then you have different regions. If you make the transistor in this part, on different part of the wafer, then the transistor's VT will of course have the variation. So this is very challenging. And but on the other hand, if your transistor gate area is kind of large, then you can cover quite a few regions. Then you can partially polarize the gate stack. Then this becomes the fundamentals for the multi-level operation. Because if you only have one domain and you point it up and point it down, you only have two states. But if you have many of them, then you can change the polarization partially, because different domains may have different critical field to switch. So depending on the voltage you apply, you can create this partially polarized states. Therefore, you can create the IDVG gradual shift. So here are some data showing that you can fine-tune this threshold voltage gradually, and so then you can get multi-level states. Okay, so then those are the fundamentals so far, and I will continue with some of the device basics. So one of the device physics that we discovered in our lab is this called this history effect in the minor loop switching. So that is when you look at the P versus the voltage, then you can have different multi-level states, as I mentioned earlier, due to the partial polarization. But then how do you switch between those intermediate states, depending on the voltage waveform you apply? So for example, we have a larger loop, which is a blue curve. So here we start with the ground state, S0, and then we press up to here and comes back to S3. And then we can switch back from S3 to S2, and then from S2 to S1. So the device will follow the blue trajectory. But we can also design a waveform with this kind of smaller loop, which is a red one. So then we can still start from S0, but directly go to S2, and then from S2 back to S1. So here you see that for the same transition from S2 to S1, in the larger loop, we need the voltage VD. In the smaller loop, we need the voltage VC. So VD does not equal to VC, even for the same transition from S2 to S1. This is because the switching voltage depends on the history of the device, whether the device has gone through S3 or not. So this is called the history effect. And of course, this is a simulation from the super precise model. But we did the experiments in our half-ion zirconium oxide sample, and we tried different conditions. We do see the differences in the switching. You see here the differences in the switching voltage. And also we tried different switching polarity. So on the positive voltage side, we also see similar behavior. And the different pulse width, that means the switching sweeping frequency. Then we also see these differences. So then this seems universal in the FeCAP. And also we tested the same behavior on the global foundries 28 nanometer FeFET. And here I won't go into the details of this operation. So basically here we cannot measure the polarization directly, but we measure the drain current from the FeFET. Then we can do this smaller loop and larger loop switching by detecting the drain current. So here we get a similar history effect. For example, here we look at this column. So for the larger loop, let's say from the S2 to S1 state switching, here we need a negative 2.8 volts. But for the smaller loop, for the S2 to S1 state switching, only need a negative 2.5 volts. So this is different switching voltage. If we use the same 2.8 volts here for the smaller loop, then we will get a different state. So here you see that if we do not use this one, use a 2.8 volt instead. So then after the programming, then the conductance of the device become like 11 nanosiemens. This is different from previous one, which is like 0.19 microsiemens. So it's like 10 times smaller. This is a different state than this one. So if you want to achieve the same state, you have to use different voltage. So then what causes this effect? We did a lot of device physics study. And here we can use this so-called time-dependent Landau-Ginzburg equation to simulate numerically by solving the partial differential equation. And then you can simulate the domain flipping process. So here we assume this assume the ferro thin film has many domains, and each domain may have different critical field to switch. So here then we can simulate the switching behavior initially from the S0 state or the dipoles down. Then we go to the S3 and come back to S2 and then eventually to S1. Or we have the smaller loop, go to S2 directly and then come back to S1. So here you see from S2 to S1, the net polarization or the average value of the polarization is very similar of this S2 and 2S1 states. But here, the voltage you apply, or let's say normalized electric field you apply will be different. In this case, you need a negative 0.8 volt, 0.8 is uniformly, it's normalized. This is 0.6. So here the reason is that you look at the internal configuration is different. Even though externally they have similar polarization, but internally you see that the pattern is different. So they have different internal states. So this is a reason that we cannot trace the switching in this minor loop. If this is still very difficult to understand, then let's use a simple toy model to understand this better. So let's simplify the picture like this. We only have 6 domains. And then let's say the left one has the largest pulse field, the most difficult one to split. Let's say this is hard domain. And then on the right, this is the easiest domain to flip. Then here in the larger loop, let's say start from the ground state, all the dipoles up. And then here you apply like a large voltage. Then we flip 10 of the dipoles down. So we will flip both, the easiest from the easiest one first. And then gradually, let's say, flip 10 dipoles down. And then go to the S2 state. We flip 4 dipoles up again. So here in this S2 state, in total, we have 6 up and 6 down. So the net is 0. So the net charge is 0. And then for the minor loop, we directly go from here to here. So we are going to split 6 easier domains here. So again, in this S2, we have 6 up and 6 down. But if you look at the internal configurations, they're different. So in the next switching to the S1, we want to flip 2 more up. So here we will start with those 2 here. But those 2 is more difficult than these 2 to flip. So that's why here we need to use a larger voltage than this one, because here we have easier domains to flip. So that's why here you have to track the internal configuration, which is not possible by measurement, because this internal configuration is not possible to measure from the electrical measurement point of view, because externally you will get 0 net charge in those 2 S2 states. You think they are the same, because the net charge is 0, but internally they are different. So there's no way to track unless you do the simulation or the toy model like this. So this will cause the trouble for the neural network training. If you want to switch between those intermediate states, then you will lose the track. So then the suggested mitigation strategy is always erase before program. That means always, let's say, if you want to switch to the intermediate state, you have to go to the ground state first. You always apply a large negative pulse to make the device goes back to S0, then go to the intermediate state. So do not switch between those 2 intermediate states. Always go back to the ground and then go up again. Then you can deterministically program to the intermediate state. Do not allow the intermediate state to transition from each other. Otherwise, then you will lose the track. So then with this strategy, we can recover the training accuracy for this even small data set. And of course, this comes with additional overhead with another program or erase pulse. And then let's talk about the array level operation. So in the array level, for the FeFET, we have to program and erase individual cell if you want to do this in situ training. Because normally, if you look at the flash memory array, then you do not do the block erase. So you erase the entire block. So all the data will be read to 0 at one time. But here, if you want to only write individual cell, then you have to do a little special operation, because here all the transistors body are shared from the substrate. So if you apply voltage to the body, you are going to erase the entire block. So you cannot erase from the body. So here we have to do this so-called drain erase to apply the erase voltage to the drain of the transistor. So let's look at this in more detail. So here, this is a waveform for the testing. And then you can think this is a configuration we are going to use. We are going to ground the gate and then apply the drain voltage to erase. So initially, the current IDVG, the current is high, but then as we ramp up the VD voltage, from 1 volt to 3 volts, we can progressively reduce the current. So that means the erase is successful. So the erase is voltage coming from the drain, not from the body. Because for individual device, yes, you can apply positive voltage to the body. Therefore, you create a negative gate voltage equivalently. But here, as I said earlier, if you apply a positive voltage to the body, then the entire block will be erased together because the body is shared. So here we have to apply the drain voltage individually. So then we tested this on the global boundary wafers and back changing the combination of the drain voltage and the drain pulse width. And then we can erase, from the drain current 1 micron to the drain current like 0.1 nanoamp. So we reduce the current by 4 orders of magnitude. That means the erase is successful. But this comes with the condition that we have to bias the source to be the half of the drain voltage. And then we found this is effective in the FD-SOI device, but not very effective from the bulk device. This is because in the FD-SOI, the drain voltage will penetrate into the channel because the channel is floating. But in the bulk, there's no constraint to the body. So if you apply drain voltage, the drain voltage will be, the field will be terminated to the body. Then it's not very effective to raise the channel potential. So we need to confine the geometry of the channel to erase. So here, not only the erase, but also we need to consider the unselected cell in the array, because in the array you have some cells to be programmed or erased, but you have other cells along the same word line or along the same bit line, and those will be unselected. Those cells need to be inhibited from being programmed or erased. So here we have to inhibit. For example, here we apply like a inhibit voltage, like half of the drain voltage to the gate. Then this cell will not be erased. So here we repeat this for like 10 to the power 6 cycles of the erase, let's say with this configuration. And so for the erased cell, we're going to have 0 voltage here, but for this inhibited cell, we have 1.5 volt voltage here. So in this configuration, we keep applying the pulses, then still the drain current is high. That means it's not being erased. So this is inhibition. So here we discuss how we operate the FeFET in one array. And finally, let's look at the variability and scalability. So the challenge, as I mentioned earlier, is because as you grow the ferroelectric thin film, you have this variation across different locations of the wafer. So here, if we measure this from so-called transmission Kikuchi diffraction methodology, then you will get the p-value, the polarization, the surface charge at different locations of the wafer. So if you make the transistor in this location or in other location, you have different VTH or different behavior. So here, what we do is to take this imaging from the SEM and then do a TCAD simulation to predict the IDVG if the device is fabricated in this location versus if the device is fabricated in this location. So here we are going to treat this with a pixel, like 7 by 7, because here like each pixel is 4 nanometer by 4 nanometer. So this is like 28 by 28 nanometer in terms of the gate area. And then we have so many devices from this wafer. So if you do the TCAD simulation, you will get this IDVG distribution depending on the location of the wafer of the device. So if somehow all the tables are up, all tables down, you get the most left or most right IDVG, or if you have the partial up and partial down, you have somewhere in the middle. So here then, if we do the TCAD simulation, this will be very slow for, let's say, tens of thousands samples. You get on that, you will run the simulation for 1 month. So then, how do we speed up the simulation? So here we use a machine learning technique to treat this as an image classification problem, because here the input essentially is the 7 by 7 image, pixel image, showing the polarization variation map. And then we treat this as image classification problem. So we try to build a neural network model to predict if the input image is like this, then what is the output of the characteristics? For example, the VTH, high VTH, no VTH state, subspatial slope, incurrent state. So input, as I said, is a pixel. Like 7 by 7 pixel, you convert to like 1 by 49, and let's say 49 input value, and then the output is those metrics. So we build a neural network model, and then we use the TCAD values as a training data set, then train the model, and then after the model is complete, then we can predict. We do not need to rerun the TCAD simulation anymore. So then we can just predict given the input image, which is a space variation map. So here we show some calibration between the TCAD and then the predicted value for the high and low VTH state for 500 samples, and it will show the correlation. So if you use enough data for the training, then you can have a perfect matching between the machine learning predicted threshold voltage versus the TCAD generated threshold voltage. So after the model is done, then you don't need to rerun the TCAD. So later, let's say if you change the process, you get a new sample, and then you redo the imaging under the microscope, then you get the new map. Then you use a machine learning model to predict if we fabricate the devices using the new sample, then what would be the 3 sigma for the high VT, low VT, and the unstable current subspatial slope. So here the prediction compared to the TCAD generated value will show only like 1%, 2% error. But the simulation time is much reduced when estimated for, let's say, 10,000 samples. If we run TCAD in our server, it will take like 780 hours, like, almost 2 months to run that. But if we run the model, then it's pretty quick because it's only a simple neural network. So within a few minutes, we can get the results. So here, then we also did the TCAD simulation to scale the FeFET towards 3 nanometer load. That means we have to change it to the nanosheet structure. And one way to reduce the write voltage is to make the ferro do not surround all the gate, but only just on the top. Then due to this so-called cap area ratio, then we can make sure most of the voltage drop on the ferro instead of the MOS tab underneath. So then this could improve the write efficiency. Therefore, we predict that at 3 nanometer load, we can write the 4 nanosheet with only 1.2 volts programming voltage. Okay, so then this is halfway through, and if you have any questions, I can take a few. If not, then we will continue the second half, which is the application. So if you look at the AI model today, there are 2 classes. One is the megabyte level for image classification, and the state of the art is like the ResNet. So here then it's typically like tens of megabytes, even for the ImageNet. And then if you look at the other space, which is the gigabyte level for the language model or graph model or the recommendation system, it's easily get up to like hundreds gigabytes for today's GPT-3. GPT-4, even OpenAI didn't disclose what's the size, but GPT-4 people predict it's like 1 terabyte. And also Facebook, the deep learning recommendation system for the their advertisement social network recommendation, it's like 1 terabyte. So this is a huge space. And then we think we have to use different technology platforms to accelerate these different applications. Let's say for image classification, a megabyte level. So for inference, we can use the ferro to do the inference because as you showed earlier, GlobalFoundries already demonstrated 32 megabit FeFET array. So we can reach that capacity. But for the gigabyte level model, there's no way to use any embedded memory. And like the FeFET, and the normal FeFET, I mean, like the Global Foundry used on other technology like RRAM, MRAM, there's no way to get like gigabytes. So this is a play by 3D NAND only. And here the Ferro has a very good chance to be used in the 3D NAND architecture. Because as I said earlier, the FeFET is very similar to today's charge trap transistor. The only difference is the ferro peak dielectric versus the charge trap peak dielectric. And then the operation principle is similar, VTH shift, although the shift direction is opposite. But let's say that the fabrication is very compatible with today's 3D NAND. So 3D NAND, could reach this density. But this is only for inference because this is pretty slow 3D NAND. So for training, still I think we have to use DRAM, HBM, or new version of DRAM. So here, then let's look at the megabyte level model inference. And we believe that we can use this capacitive crossbar array for in-memory computing for this megabyte level problem. And here in our group, we propose a new way to do this in-memory computing, not in the resistive crossbar, but in the capacitive crossbar. So here, let's say what we have is a capacitor in the crossbar array. Compared to in the RRAM theory last lecture, we show the chip we designed with TSMC RRAM technology is 1T1R, and then we do the current summation along the column. But then we figure out some challenges in the current domain computation because here, if you sum up the current, then you will spend the static power. If the input voltage is high, then you are going to pay the dynamic power to charge up the VLAN. And once VLAN is charged up, then you flow the current, then you consume the power. And this will cause the IR drop because you have the current flow, the bitmap, and series resistance will cause IR drop, voltage drop along the bitmap. And then this is not very good. But if we can somehow use a capacitor to do the computation, so here you see that capacitor, there's no DC current flowing through the capacitor. Only the rising edge will have some transient current. So we only have the dynamic power. We get rid of this part at all. So it's much more energy efficient. And since this is open circuit in nature, so there's no IR drop along the wires. So essentially, we want to switch from this current domain computation to the charge domain computation. And then in our lab, like 3 years ago, we discovered this non-volatile ferroelectric tunable capacitor behavior. This is a small signal behavior. So in our initial demonstration, we have this ferro cap, HZO, coupling zirconium oxide between two tiniated electrodes. And then here, if we measure the small signal CV, we will, let's say the epsilon with a dynamic constant, or let's say the C versus V. This is a small signal measurement. So here at 0 voltage, then we have high capacitance state and no capacitance state. So we can use the different capacitance values to encode the data. Let's say data 1, data 0. So this relies on the asymmetry of the CV, which is weird actually, because ideally, if you have a capacitor like this, because the structure will be symmetric, then the butterfly curve, as I showed earlier, will be symmetric. So at 0 voltage, you should not have a gap between high and low capacitance space, ideally for a symmetric structure, because there's no way to differentiate. And let's say you have small signal from the top or small signal from the bottom, it should be the same. But somehow, if the device has some internal, defects, especially in the bottom electrode, because of plasma enhanced AOD to do the coupling zirconium growth, then the plasma may damage the surface a little bit. So we have more oxygen vacancy here. Then oxygen vacancy typically positive charged. Then we can have so-called the domain warping effect. So because we have positive charge here. And some of the domains will be pinned down like this, or pinned up like this. So then after the positive sweep, we still have some domains that is like this. Then we'll have the green domain boundary between those two. So with a small signal at 0 DC voltage, then what you do is to add more charges to the plate. Then due to the domain wall motion, and then you are going to expand this domain and then suppress this domain when you have a negative delta V on the top electrode. Then you get additional charge due to the domain wall motion. So this additional charge, this is a transient behavior. This is interpreted as higher capacitance. So that's why here we have higher capacitance. But if you have no domain wall after the negative sweep, then it's here, then you have lower capacitance. So here we rely on the asymmetry of the interface to create the CV asymmetry. And then at DC 0 voltage, we can have high and low capacitance states to store the data. So this is like a programmable and tunable capacitor with different capacitance states. So here then we can cycle it many cycles. Like here we repeat for like 10,000 cycles, still the behavior exists. So then with this device, then we can do this vector matrix multiplication in charge domain. And this is a circuit level operation. So let's say those capacitors will be proven high and low capacitance, representing your data 1 and 0. So you have a weight matrix be stored in the cap array. So here, when you do the computation, you have to do it in two phases. The first one is to enable multiple rows depending on the input vector. If the input vector is 1, then you turn on the row. If it's 0, then you will make it floating. And then you basically you are going to charge up the capacitor depending on the input. And then the second phase, you are going to ground the input to common voltage. And then here at the end of the column, we have op amp. And then you are going to force the charges on the capacitor to be transferred out. And then through this feedback capacitor, we call it CREF, to the output of the op amp. So here, if you do the circuit analysis, you will get the output voltage in this equation. So essentially, output voltage is the input voltage times the column capacitance, modulated by the column capacitance, then divided by the CREF. So then this is essentially the input vector multiplied by the weight matrix. You don't get the output voltage vector here. So this is a charge domain computation. We charge up and then transfer the charge out. So experimentally, we have demonstrated this operation using our fabricated crossbar array with those capacitors. So here is a small demonstration with 12 by 12 crossbar array. And since we do not have the preferred circuits like the op amp from university clean room, so here what we did is to have this crossbar array with the probe card system, and then we have other this preferred circuits like op amp, CREF on the PCB board on the board level with the discrete components, and then with the instrument you can measure the entire operation. And for this, say the two-phase operation, charge up and the charge transfer in the entire system. So here we demonstrated the operation. So let's say your output voltage proportional to the number of inputs that is in, number of the capacitors that is in the on states or high capacitance states, or this output voltage is proportional to the number of inputs that is 1. So here we show that the output voltage could be calculated using the input vector and then the weight matrix. So this is a small demonstration, but we show the possibility using this charge domain computation. And then if we want to scale up the system, we have to do some simulation or projection benchmarking. So here, let's assume we can increase the size to 128 by 128, and then design this entire circuit at the 22 nanometer node with op-amp and so on. Here we have used a very simple op-amp to minimize the overhead of the op-amp. So here then we do the simulation, transient simulation, noise simulation. Because one challenge here is the thermal noise. You have cap, then you have thermal noise. The noise with the cap is the noise level equals to KT over Q, also KT over C. Then that is the voltage of the noise. And so then here we did the simulation, and I will skip the details. But I just want to point out that the energy to read out this 128 by 128 array is only 0.1, first 0.1 picojoule. But if you do similar thing in R-RAM, M-RAM, or even FeFETs, you will have much higher energy because those will be current domain. But here we are doing the charge domain. So the energy is only spent for the transient operation. So this is a benefit of this capacitive design. So here then one challenge in our demonstration is that, let's go back to here, initial results. You see here the on-off ratio is pretty low. So let's say on state epsilon at 27 and off state 24. So let's say the ratio is 1.2, maybe 1.2. So it's a very small sense margin. So we cannot, if there's a variation, then we easily disturb the output. So how to increase the capacitance on-off ratio? So here, as we demonstrated earlier with MFM, a metal ferrometal cap, even we have some asymmetry due to the interface property. Still, this is quite symmetric structure. So if it's perfectly symmetric, then the ratio would be 1. There's no, basically there's no gap between those two states. So here we have to explore more asymmetric electrodes. So let's just do an extreme case, MFIS structure, let's say with FeFET. So the other electrode is not metal, it's MOSFET, right? So metal, ferro, interfacial layer, and then semiconductor, the silicon substrate is another electrode. So with this configuration, it's very asymmetric. And then if we measure this configuration, if we float body and measure the let's say gate, and then ground source and drain together, then we measure that we get the blue curve in the CV, in the small signal CV. You see this blue curve, then we have a large window at 0 volts here, more than 20 or 25 in terms of capacitance here versus here. So this could help with NV cap design, and we validated from glue foundry wafer we have. So we just ground source and drain when we measure the capacitance. So here, then what is the mechanism of this NV cap effect in the FeFET? So this is what we propose. Essentially, if you look at the on state, when you have all the dipoles pointing down, then here you will induce the channel inversion. So therefore, the total cap is the channel inversion cap plus the overlap capacitance CGS CGD. So that's your total on state. And then for the off state, you polarize all the dipoles up. Then here you have the a depletion of the channel. Then you don't have charge. Then here you only have this overlap capacitance. So C off is essentially the overlap capacitance. So then you can imagine the on-state on-state capacitance will be proportional to the AKT area. So this is indeed what we measured from the wafer. And then for the off-state, it will only depend on the overlap length. So here for different gate lengths, then the overlap distance decrease a little bit, but do not change it too much. So then the C off is only depend on the gate overlap. So here we measure the smallest sample from the wafer is like 1 micrometer square we can measure because this already reached the noise flow of the experimental setup. It's very difficult to measure any capacitance below 1 femtofarad because the noise of the off-chip measurement. But at least for 1 micrometer square cap, we can reproduce the results. And also we measure different, on the global foundry wafer have so many devices. So we measure the statistics, and we can see that with the scaling, then the distribution will be spread out a little bit, but still is pretty close to the center of the distribution. The variation is pretty small, only like 1 or 2%. And also we validated the proposed mechanisms through the TCAD simulation. So we try to reproduce the device structure by TCAD, and depending on the dipoles pointing up and pointing down, then we can have the channel inversion or channel depletion, and then we can simulate the CV. And this is the simulation result, and this is the experimental result with similar, the same gate length, and you see that we can reproduce the behavior from the data through this TCAD simulation. So this verifies the proposed physical mechanism. And also we can further optimize the on-off ratio, because here with the TCAD, we can change, the gate overlap length, then we can change the C-off. And then in principle, we can get larger than 100 on-off ratio in terms of capacitance, if we can change the device structure in the future. But right now, since the global boundary wafer is prefabricated, we cannot change anything. So here the measured on-off ratio is about 20 to 30. So here we are aware of the challenges due to the device-to-device variation and also the thermal noise. So we did some simulation for this kind of, vector matrix multiplication with this ferro cap. So if the cap, like the variation is like 1%, then the output could be distinguished different levels. But if the cap, each cap, the capacitance has 10% variation, then you see that it becomes challenging to distinguish the output voltage levels. And also the thermal noise will further add errors to the output. So here we build a simulation framework to evaluate the impact of non-ideal effects like limited on-off ratio, device-to-device variation, and the thermal noise. So then we configure this, convert all those to the signal-to-noise ratio as this output, and then this compared to the this becomes the effective noise of bits, an effective number of bits for the partial sum, and then we can do the neural network simulation with the noises to the partial sum, and then we can evaluate the accuracy. So here are some results. I won't go into the details, but depending on the, let's say, the on-off ratio and how many rows are turned on simultaneously, then we have to wait for some, let's say, time for the charge to fully transfer out. But with proper design, then we can still get good accuracy, over 91% for this FeFET accuracy. So here, this really depends on the number of rows that are turned on, and also the device on-off ratio. So here you see the device on-off ratio is low, like 2 in our initial demonstration from our MFM cap, then the accuracy will be very bad. But if we have 30, as we demonstrated in the global boundary FeFET, then we can still have good accuracy. All right, so then this is what we believe to be the ultimate megabyte level inference design with a ferro cap. And then next, for the training is a little bit more difficult. This is because training needs higher precision. For the inference, which just need low precision, like 1 or 2 bit is good enough for inference, especially for small model. Even for complex model like ImageNet, like 4 bit, easily we can do the inference. But for the training, even for small data set, you need 6 bit. For more challenging data set, you need 8 bit or even 10 bit. So the requirement on the training is much more stringent than the inference. So here the idea is to use a hybrid precision. Let's say for the training, we use high precision, and this high precision comes from the volatile mode to store the LSB, needs the significant bits. Let's use one example. Let's say if we want to achieve 6 bit weight, And then we can represent the 6-bit weight in 2 bits in the non-volatile memory mode, plus 4 bits in the volatile mode, for example, on a capacitor. So here, this is what we proposed to demonstrate this idea. So we use FeFET to the prioritization of VTH state to store the MSB. So here we can program the FeFET into 4 levels, and then we can store 2-bit MSB. And then that means in IDVG curve, we have 4 curves representing those 4 levels of the VTH. That is a 2-bit MSB. And then for the LSB, we are going to use this charge and discharge transistor to charge up the gate capacitor of the FeFET. So here then, this will represent 4 bits LSB. So in other words, if you look at the IDVG, then we are going to have different segments correspond to different MSB, but within one MSB, then we can continuously tune the current by charging up the gate a little bit. If we charge up the gate, then gate voltage will increase a little bit. So we can have some more bits using this dynamic tuning of the gate voltage. But this is the volatile mode because the gate voltage, due to the leakage of this transistor, then this charge eventually will leak out. So this is in the volatile mode. But this is good, okay for the training because the LSB will be updated frequently anyway. So what we really care about is after the training, we only memorize the MSB. So which big segments are we in? So this is the training results. We only need to remember the MSB. But during the training, we're going to fine-tune the LSB by charging up and down of this transistor. So with this approach, then we can equivalently realize 6-bit operation. And then we can get this pretty linear potentiation and depression. So this will help with the training accuracy. So here you see that the training accuracy is very sensitive to the nonlinearity and the symmetry of this conductance versus the training pulse. And then with this kind of 6-bit equivalent weight for the CFA10 data set, we can achieve 90% accuracy. And so this is pretty good for this one transistor, let's say one FeFET plus 2 transistor solution to represent like 6-bit weight. Okay, so the last topic for today is 3D NAND. And as I mentioned earlier, so this is the only way to do the large language model today. So if we want to do the inference from there. So then, because those models will be stored in SSD anyway. So if we can pre-process some of the operations from the model, then that's good. So here we propose that this 3D NAND like FeFET computation. So we can, replace the gate stack of the 3D NAND string with the ferro. And then we can do this vector matrix multiplication by one vertical slice. If the input is from the word line, the output is through the bit line. So essentially, we can have many of those slices. And each slice, if you only look at the vertical slice like this one, then if you look from this way, it becomes a 2-dimensional FeFET already. So here then, again, how do we individually program those cells? This needs very special timing. And because, as I said earlier, we have to use a string erase to individually program and erase. So we have to bias different word line and different bit lines in certain way or in certain voltage and also in certain timing to have only the selected cell to have the appropriate voltage. I'll skip the details, but my point is that we have to do this very carefully. So here with this proposed timing for all the control lines. You have the selected cell, word line, selected SSL, selected unselected word line, unselected bit line, selected bit line, and so on. So we have to use this very special timing, and then we have done the space levels netlist simulation with the FeFET model. Then we can make sure only the selected cell has enough voltage to trigger the change of the privatization. So this is a very complicated control. And then for the 3D NAND, then we have the engineering the FeFET a little bit different from Global Foundries approach for the embedded memory. Because for the 3D NAND, if we want to make more to this 3D NAND, we have the TLC QLC operation. That means we store 3 bits per cell or 4 bits per cell. So we have to increase the multi-level states in the FeFET as well. One straightforward way is to increase the thickness of the ferro stack, but it's not straightforward. Use a ferro for the half oxide system. If it's thicker than 20 nanometers, then the ferro behavior will disappear. So here we have to use the superlattice stack with the ferro, dielectric, and the ferro. Then we can still maintain the overall stack as a ferro. But still, then we can get in like multi-level states. So here by the TK simulation, we demonstrate 3-bit operation. And then we consider the variation of those ferro versus the dielectric phases. And then we can still get the distinguished memory window in terms of the threshold voltage distribution. So this is through the simulation. But recently, our group has collaborated with Professor Sumedata and Professor Asif group at FeFET. We experimentally demonstrated this concept, and we will present the experimental data at the upcoming IEDM conference as well. So here, this is one way to engineer the FeFET for the 3D NAND. So for 3D NAND, there are many ways to use it as computing memory, depending on the input and output direction. So one way is to use the input, have the input to the bit lines, and then have the output from the source line. So here we can have because normally in 3D NAND block, you have very, very large number of bit lines in one block, let's say 10,000 or even 20,000 bit lines in parallel. So you can have high input parallelism. But then the tricky part is that here we have to redesign the 3D NAND peripheral circuits, because at this 3D NAND, after the source line, there's no peripheral circuits. But in this case, we have to add the ADC to the source line. Or we can use the SSL or WL as input. Then in this case, we are going to have input from either the SSL or from the WL, and the output is measured from the bit line. Then the output has high parallelism. This will cause more switching energy, because here the bit line is pretty long. The SSL line and then the WL is pretty long, because number of bit lines is very large. So then if you charge up with SSL, you are going to have high charging switching energy, dynamic energy, charging those SSLs. So here anyway, so we have done some initial design with this bit line input for the vector matrix multiplication. We have modified the circuit a little bit for 3D NAND, have added ADC and so on. So here I'll skip the details. Again, we use our neural sim benchmark framework, which I will have more discussions in the next week's lecture. So this is open source tool that we evaluate those peripheral circuits for the computing memory platform. So we can have the models for ADC, adder, shift register, and so on. So then we can evaluate the entire system's PPA, power performance area. So here, then for the 3D NAND, then we still need to deal with the device non-ideal effects. For example, if the NAND string has the device variation, so you can get different string currents, and then after the ADC, you will get the errors, and then we have to evaluate the accuracy. For example, C-button data set as a function of the sigma of those distribution. So then we have to use some redundancy in the input, and then we can still get good accuracy. So there are some tricks to make this work. So here again we have to deal with the device non-ideal effects. And then we use this 3D NAND approach to do other applications beyond the image classification, because even though in the previous work we use image classification as the initial toy model, but as I said, image classification model does not need the 3D NAND. You can use R1 FeFET or the FeCap, as we discussed earlier. It's only megabyte level model. And then for what is interesting is the large model, like gigabyte or terabyte model. Then we can use a 3D NAND. So here one application is bioinformatics, and one example is the genome sequencing. The DNA. If you want to match the DNA to the certain class, then you have to do this matching process with those ATCG labels. And then one example is for the COVID virus matching. There are so many variants, for this one. So we have to match this one belong to which class. So then for the data, we have to do the matching, and you can store the classes into the 3D NAND, and then use the 3D NAND as associative memory. Essentially, we do this like in-memory search, and then we can compare the input, which is a pure vector. This is the unknown data, unknown virus, to the existing virus, which is already identified, stored in the 3D NAND, different classes, and then you compare the bit and voltage, and then the data pre-stored, and then you result in different number of string currents. Then you compare which string will give you highest current, that means the closest match. So here then, because the data volume is so large, and so here then we have to use a 3D NAND. Otherwise, if you use other approach, you have to first get your stored data from the SSD to the DRAM to your CPU. Then the data transfer will cost a lot of energy already. So here, if you can do this directly with a 3D NAND, where you store the data, then you don't need to move the data. So here, this is a key idea with this 3D NAND in-memory search for the genome sequencing. And also, there's graph model. Graph model is also very large, and the graph model is a little bit different. What you care about is not only the connect weights between the nodes, but also which nodes are connected, because it's not fully connected. So we can reconfigure the 3D NAND to store the destination or the connection and between those graphs, and then we can do the graph processing. So here is another application that could demand large memory capacity. And finally, I want to point out that 3D NAND is a slow process, essentially. And 3D NAND flash memory is much slower than DRAM than your processor. So for the processing, after the 3D NAND, for example, we have the peripheral circuits like ADC, register, adder, timing control, and so on. So we do prefer to fabricate those peripheral circuits in logic process instead of the 3D NAND process by itself. And then what we can do is to integrate, let's say, the 3D NAND wafer with a logic wafer through the bonding. And this is a heterogeneous integration. And 3D NAND can still use a 3D NAND maximum thunder array, and then have high voltage transistor built into the 3D NAND wafer. And then the logic could be produced by another logic foundry. For example, 3D NAND you can do it with the memory vendor like Samsung, Micron, and so on. And then the logic then fabricated by TSMC, for example, and then somehow you can magically bond those two wafers together. Then you can have the best system level benefits because the data transfer could be directly from the face-to-face bonding. So today, the hybrid bonding technology has been progressed, has been developed from the industry. So there are many opportunities in the heterogeneous integration. And I'll skip the discussions for this one for now, because I think the last lecture, 2 weeks later, we will talk about the 3D IC design. And one of the new interesting area is the 3D IC with this hybrid bonding. Okay, so then I will summarize, and today we talk about Ferro, basically, and we believe Ferro is a good candidate, enables a computing memory. So for the training, we have to use this hybrid approach, Ferro plus the volatile capacitor. And then for the inference, then we can either use FeFET or use our crossbar capacitive sensing. So if we want to use FeFET, then we have to be careful. For the multi-level states, we have to avoid the history effect and do the erase before programming, and also use the drain erase to program the individual cells. And then GlobalFoundries has been a pioneer in the FeFET development, and they have provided the risk manufacturing for FeFET, and we had partnership with GlobalFoundries, so we get their wafers, and now we are designing the chip with the GlobalFoundries platform as well. And then if we want to scale further to more advanced node, we have to consider other geometry from FeFET bulk with a FinFET to even the nanosheet. And so this is on the roadmap. And eventually, if we want to, for large scale AI model, then we have to work with the 3D NAND, and then we have to engineer FeFET for the 3D NAND, which may be different engineering approach than the embedded memory. If you want to make it compatible with GlobalFoundries or even other foundries, advanced logic platform, then the engineering is very different here for the 3D NAND version of the FeFET. All right, so I think that's pretty much for today's lecture, and I'll stop here and answer some questions.
感谢于老师。那我们就看看那个同学或者我们老师们有没有一些问题想要跟于老师这边交流或请教。
于老师您好，我这边是长庚资工系年景夫，想跟您请教一下3个问题。
好，
就是第一个问题想请教，就是说您像上周提到RAM，以及这周提到的 FeRAM 或 FeFET，那这个就是说虽然您刚刚有提到，就是他说可以跟这个 CMOS 的这个 backend of line 去做一个制程整合。那我们也会蛮好奇说，就是它这样子的整合的容易性，例如说它是只要因为它只要加上几道的这个制程，还是说它需要一些比较复杂的这个，例如说要把它帮领出去 ，I don't know， 就是它会增加多少的这个整体的 cost 这样子。那对，这是第一个问题。那第二个问题，
那我先回答第一个问题。那我们一个一个来。
好。
这个关于这个制程的这个就是 added cost，是这样，如果是你在 front end 的 integration， 比如说 GlobalFoundries 他们做的，因为我跟他们有合作，所以其实在他们的 mask 上面，他们只需要加2道 mask， 在那个 gate 那里就 define 这个 gate 是一个ferro 的 gate， 所以他们那个 cost 不会太多，只需要加2道 mask。然后这是 front end of line integration， 但如果是在 back end of line， 那你就在 back end of line 再加可能2-3道 mask， 我觉得 OK 了 back end of line。所以总体而言，这个 cost 不会有太多增加，就是2-3道 mask。
OK， 所以这个 cost 就比较不是大家主要的 issue 这样子。
对，这个不是主要的 issue。对，
谢谢。那第二个问题想请教，就是说当然这2个礼拜介绍了很多 technology 啦，那就是说假设我今天假设要挑一个去做 computing memory， 那当然不同的应用可能适合不同的元件。那但是就想说，于老师会怎么建议说，怎么样的情境下我适合，例如说使用 RAM， 那什么样的情境下我适合使用 FeFET 或 FeRAM 这样子？
上周我也回答了这个问题，如果是 high performance computing， cloud server， 那你还是用 SRAM 比较好。with 这个3 nanometer SRAM， 比较好。digital CIM 比较好。但是如果是这种 edge device， 然后就觉得这个可能性就多一些嘛。这个因为 edge 这个当然也是取决于你的 accuracy 需要多少。但是对于 edge 来说，那你就是 cost 比较重要了。那你就是这些22、28 nanometer platform 就比较好。然后这些里面可以用的就是比如 RAM， ，R run 因为现在是Foundry已经有提供嘛 ，TSMC 已经有 R run，当然，它不会给小的这些学校给这些的但是大的 customer 它是可以有的，当然我跟他们有合作，所以他给我。但是就是说，如果对公司来说，你可以是用这个，比如说22 nanometer R run 来做这个 edge 的这个 inference，with a non-standby 这个 application。但如果有 Ferro，那更好了 Ferro，因为 intrinsically Ferro 的这个 device performance 会比 R run 更好。就是不是说它这个 endurance 或者其他会更好，它有一点优点比 R run，两点优点比 R run 好，第一个是，如果不用我说的那 ferro cap，那个还 very early stage，也是我们 lab 提出来的，它就是用这个比较成熟的 FeFET，比如 Global Foundry 已经有 FeFET，虽然他们没有真的是这个 volume 的量产，但是他们有些小 volume 的 low volume 的这个 manufacturing，但就哪怕是以 Global Foundry 的 ferro 来说 ，compared to R run，有两个优点，就是第一个是它的 on-state resistance 会 much lower，因为R run 我上次讲过，台积的 R run 或者不一定是哪家，那就是所有的 R run，只要是 Foundry 的 R run，不是学校的 Foundry 的 R run，它包括 M run，它的 on-state resistance 都很低，都只有 a few kilo。那你这个 current 很大，其实每个你 sum up 这个 column， 你比如说几十个、上百个 cell， 每个 cell 给你个几个 micron， 那你加起来就几百个 micron 上 million， 你这个current 是很大的 ，power consumption 是很大的。但 ferro 它的 power consumption 可以10倍小于 R run， 为什么？因为它是 three terminal device，OK， 我们随便去给一个这个 IDV 机，它是 three terminal device。所以你可以 bias 你的这个 gate voltage， 有很大的一个dynamic range 去调它的调节的这个readout current。但是 R run 你知道 two terminal device， 你的 on state 是多少，你 program 是多少就是多少，你的可调的空间很小，就是 a few kilo， 你不可能做到几十个 kilo。所以这个 ferro 你可以 bias 你的 gate， 比如说你稍微低一点 0.8 伏特，那你这个 current 就只有1个 micron， 你当然这里会有点 variation， 但是你就是 in principle 来说，你可以控制它的这个 current as you wish， right？ 那你这个power consumption 可以 much less， 这是第一个。第二个是这对于 read 来说，第二个来说对于 write， 这个 R run write energy 更大的。write energy， 每个 bit 大概10个 picojoule 吧，几个 picojoule，let's say 3到5 picojoule。Ferro 我刚才说了，你这个是 FeFET switching， 它的那个 switching energy 只有 femtojoule， 它的 switching energy 对于同样 size 来说，比如22纳米的 Ferro 的 write energy 几乎相当于22纳米的 S run 的 write energy， 但如果是22纳米的 R run 的 write energy 至少是 S run 的100倍。所以说，如果你是 write 的话 ，FeFET 的 energy 是 much less than R run， 100倍，低于100倍。read 可能低于10倍 ，write 低于100倍，就是energy 而言。所以从这个 nominal 的 performance 来说是 much better technology。当然 Ferro 本身有很多 challenge， 自己有很多问题，比如刚才我说了很多的 variation， 这 variation 的问题现在还没有解决，还有这个这 endurance 10的5次方、10的6次方也不是特别的这个好，当然跟 R run 也 compatible 了，但是 variation 我觉得是个 big problem， so far， 所以并没就是说其他方面可能差不多了 ，variation endurance 可能跟 R run 差不多，但是从刚才说的两点 write energy 和 read energy 来说的话，是 much better than R run。
谢谢，这是很详细的回答。那我也最后想请教一下，就是一直很好奇这个，因为刚刚您有展示一页这个 NeuroSync 的 simulator， 那当然我知道您未来会再介绍，但是我好奇有一个参数，就是那个关于这个 ADC， 我想应该很多人也问这个问题，就是这个我刚刚看那页投影片，它 ADC 的 area， 就是一般我们在做 computing memory， 好像很多人都会 criticize 说那个 ADC 占的 area 很大。但是这个你的投影片这一页看起来好像没有这个问题， 那想请教就是这个到底是因为这个有用什么 technology 或者什么原因，这个导致这个就是可以 area 看起来相较没有很大这个结果这样。谢谢。
这是因为相较的原因，因为这个是 NAND array，NAND array 本身很大，NAND array 的 number of word 呢是刚才说了是那个 10K 10000到2万，你要想想这个 size 就10000到2万的 bit NAND，当然这个相较于 ADC 没有那么大。可是你说 embedded memory 的话，你就是128乘128，64乘64，那当然相对而言 ADC 就大了。对 NAND 来说，你知道一个 array 是很大的，
但
这是相较而言。
是，但我因为我是看了一下，像它这边 AZ 好像反而比 accumulator 还要再小，就是这个部分，对，也是
accumulator 太小。
对，
没有啊，这个不是1.26 2.33吗？
对，好像小一点点，是不是？
小一点点，对，我不知道具体的这个 assumption 是什么，这个要看你的 precision ADC。比如说这个可能只有4 bit ADC 或者5 bit ADC，对不同的 application 来说，你如果 high precision ADC 那是很大，对，而且你看你是用 SA ADC 还是 Flash ADC，
是，OK，谢谢。
OK，其他还有什么问题？
于老师你好，我想请教一下，像现在这个类比这个运算啊，它是一个 current 对应一个 ADC 去做运算，还是说它可能两个 current 共用一个 ADC？
都是需要公用的，因为那个 current 做不了 match，pitch 你知道很难。因为每一个这个 cell 你想R1T1 啊或 ferro 就一个 transistor，再加一个 resistor 或者什么的，那你这个 column pitch 是很小的。ADC 那个 size 肯定是 much larger。一般来说做 tape out 的话都是8个 share 一个或者16个 share 一个，所以它output 的 parallelism 是 throughput 是有影响的。
所以它运算就是pipe 的去做运算，这样可能
对啊，
第一个
你需要
做完才做第二个。
multiple cycle 这个很难，所以为什么这个 throughput 会没有那么就理想中的那么好？当然 solution 也有了，但是我下次讲 3D IC 的时候，我有一个 part 去讲，对，我们有一个design就是你 run 还是在40纳米，你 ADC 在16纳米，当然因为我们是有这两个 PDK 了，所以那你就有这个 area。
了解。那如果是8个共用一个，那这样 ADC 是不是选择 Flash ADC 会比较好一些？还是说一样会优先使用 SA 的架构呢？
一般来说，我们建议是你如果你的 precision output precision 4 bit 以下，你用 Flash ADC；你但如果你4 bit 以上，Flash ADC 太 expensive，所以我建议用 SA。
了解。
对。
好，谢谢老师。
还有什么问题吗？这个 ferro 可能今天的 topic very to device technology 。
还有没有老师还是同学有一些问题要跟于老师一起讨论的？
如果没有，那我们就今天就先这样。
好啊 ，OK， 谢谢于老师啊。那我们就下周的话，就好像就分享那个你们的 simulation tool 了，对吧？
对。
OK， 好啊，非常感谢。就上周可能电路比较多，这周有一些 device 的 issue。 那下周的话会有一些 EDA 的 issue。
是的，是的，
好，谢谢。
好的，好，谢谢，拜拜。
OK，拜拜。